Yeah, so before starting with this video, in my last video, I received a fantastic question that I want to address before diving into today's demo of TeDDy. So first, I wanted to highlight a very important point before answering this question. So that at their heart, LLMs are not designed to be agents. So I think this is very important to understand why something like TeDDy is necessary, because LLMs basically are intrinsically trained as next token predictors. So the initial GPT models were trained like this, and in fact they were basically just hallucination machines. So in more recent times, reinforcement learning was also used with verifiable rewards in fields like coding and math to try to get the AI to produce output that doesn't only appear from the outside to make sense, but is in fact also correct. But still, from this code auto-completion, let's say, going to software development, there is still a big gap there. And basically, if we would want to train models to be effective as software development, we would need a lot of examples of long chains of action and the outcomes of those actions. And for example, current models wouldn't even have enough context window to really get all the sequences of actions and be able to learn from that. And even generating this huge amount of data, especially considering that the reward signal would be very sparse, is not something that is really feasible right now with the current paradigm that we have. So I don't believe this is the way forward for AI-assisted coding. So this is where we can take a cue from human progress throughout history. What we see is that advancement of human civilizations were not something carried by single individuals learning everything from their own experiences. So let's say modern software developers as well, they don't invent their methodologies and their way of working each time from scratch, but they rather iteratively refine methods which are passed through generations and improved over and over and over again. So applying this to LLMs, the idea behind TeDDy as well is that we shouldn't expect them to figure everything out on their own. It's not feasible, as I mentioned. And instead, we could already give them very specific instructions to basically operationalize our collective experience in software development. So the actual question that I got in my last video was why not basically just use something like Cursor with custom instructions. So I think this is a great question because I myself started experimenting this way, but I moved away from this eventually for a couple of reasons. So first of all, and I think it was the most obvious one for me, was to avoid vendor lock-in and to have greater control over the process. So for example, Cursor and all the other AI tools already provide the LLM with a lot of built-in instructions, and these can really pollute the context window and conflict with your own instructions, making it very difficult for the AI to follow your specific instructions. So when trying it myself, I was struggling even to get the AI to write tests before writing the implementation of those tests on its own without me basically needing to prompt it to do it each time. So I really wanted something where the strengths of the LLM could really come in, and one of these strengths is the ability to follow instructions. And at the same time, another, let's say, paradigm that I've seen becoming more and more popular being specs-driven AI development. So I think this is also a flawed approach because it forces you to know and to define everything perfectly in advance, which anyone who has worked on a real project knows is a fool's errand, because software development is really an iterative process and process of discovery. So locking yourself into this rigid upfront specs really kills this flexibility to learn and to adapt. Is time goes on. So this is where TeDDy takes a different approach. As you will see in this demo video, the workflow is built to create a maintainable code base from the very beginning and to work in iteration. So instead of just acting out one action at a time, it shows you the planned next steps before actually executing them. The great value of this approach is that you are always aligned with what the AI is doing. What I want to show you today is really just a quick demo of the workflow, and it isn't meant as a final working product, but I really hope you enjoy, and I would love to hear your feedback as well. So what I was thinking to do is to build a roguelike game. I was thinking something pretty simple, but still challenging enough for an AI to tackle. So the idea would be to build a roguelike snake game inspired by Vampire Survivors, and to make it a little bit challenging for the AI. We will be building it using Bevy, which is a new up-and-coming game engine built in Rust, which I find really interesting because we have always seen AI working with Python and with websites, and for that it's out of the box very good. Because it has seen a lot of examples of it, but in something more novel, for example, something built in Bevy, especially being that it has had a lot of changes recently, continuously getting updated, it makes it very difficult for normal AI coding agents to tackle this. It's still a work in progress, but I'm really excited to show you this, and let's see how it goes. First of all, if you head over to the repo, which will be linked in the description as well, you will find the two prompts that we have for TeDDy. So we have an architect and a developer prompt. You can save these in the system instructions as templates. So you will see I have one already saved for the architect and one for the dev, and you can switch between these. Yeah, let's start. This is how I like to work with it on a single screen, with VS Code on the left side and Google AI Studio on the right side open. It's very similar to how you would have in Cursor. So let's pitch our concept to the AI. So let's create a roguelike snake game built in Bevy, and this is the latest version, so 0.17.3. It should be inspired by Vampire Survivor. Something you will see is, first of all, I'm using Gemini 2.5 Pro, not the latest model, Gemini 3, because I have noticed, and a lot of other users have mentioned this as well, is that the newest model, Gemini 3, is actually not really good at following precise instructions, which is needed for this. So I would recommend you to use Gemini 2.5. Other models that I've seen working pretty well as well is DeepSeek, for example, but a lot of other models fail with these complicated instructions. So let's break down the response of the AI and how it looks like. First of all, you will see the first section it always outputs is this rationale section, and it also has this icon, this emoji, which can be either green, yellow, or red, indicating their, let's say, the status of the plan, so how much we are on our happy path and how much, let's say, difficulties it is having. So this rationale section, it's really there for the AI to reason in a structured way about what it's about to do. It also helps follow the instructions, the workflow, because you will see after it will plan basically what the next steps are. It will keep track of its state. It also helps kind of to keep this continuity during the conversation, but also if you want to basically reset the conversation, start a new conversation, you can very quickly copy the current status and pick up from there. And so, but it also helps you as a user to follow along and understand what the reasoning behind the actions is. So the first step that we do in the definition of the architecture is first to define this public contract, which we encode in the README file. Then we basically do initial project setup, and after that we subdivide the project into vertical slices. So each vertical slice is one piece of functionality of the end application. And then basically within this first vertical slice, we decompose it into components and define their interactions and de-risk also their implementation by doing a small spike test. And this spike, this is a concept borrowed from extreme programming, and it's basically the idea of not immediately working on the final product, and instead create this proof of concept first to validate our ideas. And you will see the AI will do this as a first step. So it will produce this functional spike or this conceptual spike, let's say, to test the ideas that it has about our request to create a roguelike snake game. So of course, this idea, you will see it will mention that is ambiguous, right? The request is ambiguous and we need clarification. So what we will do is to produce this first scenario, this concept. So how we go along for now, as I mentioned, it's still a work in progress. We have to execute all these steps manually. The idea is that in the future you will be able to just click and execute the commands, but still be in the loop before the actions get taken and review the whole rationale and the whole reasoning behind it before you execute anything. So in this case, we go ahead and create the file that it asks us to do. So we can see here the spike, as I was mentioning, which is basically a small experiment, a small contained experiment. And you will see basically here it illustrates the core gameplay loop that it is currently envisioning it. So we can go through this. I'll take a moment to go through this and then provide some feedback. So overall, I like this idea. The overall concept is that the player will only control direction right and left. So it will move forward, the snake will move forward at a constant speed, and we just control the angle at which we move, which is a nice concept. I didn't think about it. There are enemies appearing, spawning, like in Vampire Survivor. As we kill them and gain XP, we do not grow in length at first. And we also shoot these projectiles from the head. So maybe a concept that we could improve. So something I would do, what I would like as an idea, is to actually be able to run into itself. So right now we don't have a self collision. I would prefer being able to actually loop around enemies and actually be able to kind of encircle them and deal damage to them this way. So maybe we can refine this concept and tell the AI our feedback. So the points I mentioned here are, first of all, I want to be able to encircle. So I need to be able to pass over my own body. And this encircling mechanic basically is a way to kill enemies better or more efficiently. Each time I level up, I want to gain one additional segment. And this segment, each segment has a different mechanic. So they can be either active or passive effects that will apply. And the fourth rule I would introduce that we only take damage to the head. So basically, the body does not actually take damage from enemies, just the head does. So we need to basically avoid enemies with the head, encircle them to be able to kind of kill them. I find that an interesting idea. So let's go with that. Okay, so we sent off our feedback. Let's see what comes back as a next step. Right, so as before, rationale with green. So usually if it's green, we don't need to pay too much attention to it. Everything is going according to plan. If it becomes yellow or red, meaning that the AI, the last expected outcome was not met. Yeah, so let's look at the output. So we have another spike, and you will see actually it keeps track of all the uncertainties that it currently has. So we can go back to the first one. We can see here the current one was, how does the snake and vampire survivor mechanics merge into a core gameplay loop? and this one we just clarified. Now we have a second one, or actually we are kept on this one, so the mechanic is not yet totally approved. So actually it is updating this file, so we can go in and actually replace it with this. So we will see likely we have now integrated the provided feedback from our side. So let me review it quickly, but you will see, yes, we now have a speed torrent segment, poison trail segment, shield segment as ideas, core mechanic and circle movement and attack, and segment-based growth. So we have all these points. Of course, if I would actually be building this, we would want to look more in depth into it, but for now we can proceed. Right, so now it should be marked as resolved inside of its mental checklist. So we should see that in the next reply. So exactly, we now have another uncertainty, so about the power-ups abilities that the snake can acquire. I think we can go through it very quickly, but to show you how the AI actually works, it's really useful to show that. Like before, we see some ideas pitched, so category 1, active weapons, passive abilities, defensive segments. I will go ahead and accept this so that we can move through it. But of course, as mentioned, if this was a real project, we would want to provide a lot of more input here and refine the idea much more. How do enemies behave and spawn is the next point. So for this, we will create another spike document, and we have it here, which I believe is great already, at least for initial proof of concept. Of course, if you provide the AI from the get-go with a very detailed brief, it will not go through all of this process, but because we provided such a generic concept, it will now go ahead and try to clarify all of these points, which I think is great. It's very valuable. So we now have a document about the meta progression, which I also find very, very cool that it does this, which is great, and we can proceed. So we have 2 more left to go about procedural generation and then the UI. So you see the idea behind the whole workflow is that we do not just output a final result, but instead we go through it iteratively in small steps, and at each step we take in feedback either from the user or from the environment. So what you will see in the developer prompt, in the developer workflow is very similar in the sense that we proceed with very small steps, and at each step we prove our work basically, and we check that we are getting the results that we are expecting. So again here, about procedural generation, I will go ahead and accept this for now, but it's really interesting that it's breaking it down into these very specific subtopics. Maybe something I also needed to mention is you will see each of the replies from the AI are a series of actions. So it has different types of plans defined that it can do. So you have more insight into the repo, but basically each plan has a set of constraints, how you should do in this type of plan, and each plan has a sequence of actions. So you will see, you've seen a few actions being shown. In the UI, you can also close them and you can mark them as resolved. So right now, the prompts are really tailored for being used in Google AI Studio exclusively. Even though you can use them like from the model side, they work well also with DeepSeek, but from the interface, really, it's really tailored for Google AI Studio. The idea will be in the future to use something like LibreChat to kind of design a bespoke user interface for interacting with TeDDy, so that it's much more robust, it's much more tailored experience, but it will be very similar from the functionalities from what you have here in Google AI Studio. So as for the last point that the AI wants to clarify the UI, we can create the file. And we can see we have kind of a wireframe of the UI. So we define on the top left the health measured in hearts, the experience bar in the middle, on the right the time, and the gems or the amount of essence collected, which I'm not sure what that will be. We will see. When we have a level up, we will have a pop-up for it, pause menu, game over screen. So this looks great for me. And what we will now do is codify everything into a main README file. So now we have the main README file, which will codify the main contract, let's say, with the end user of what the game will be. So we can look at this and have a final review. But basically, it should summarize everything that we have already reviewed before. So great, let's now proceed. Let's proceed with the next phase, which is really to plan the, so now we have defined what we want to create, and now we will define how we will implement it basically. So we will break this down into first vertical slices, or one first vertical slice, and then we will proceed breaking that vertical slice down into components. So we will see how it works is that we have a main architecture file living inside of the docs folder, and you will see this structure. So basically, first of all, brief introduction of what, how it, kind of the philosophy of the architecture, which is hard-coded to favor this hexagonal architecture as a design principle. And maybe it's a good point to explain how hexagonal architecture looks like. And as the name suggests, I will try to draw this hexagon. But basically, the idea is that you have a main core of your application. So you have a domain, a core domain, where all of your business logic lives inside of this core. And what this core is only written, it doesn't have any external dependencies. So it doesn't use any external frameworks, it doesn't interact with any APIs, and it's really a sacred place, let's say, where you only define the core logic of your application. And whenever it needs to interact with external dependencies, you will define, first of all, ports inside of the core application. So let me add that here. So you will have a port as part of the core application, which then gets implemented, gets connected by an adapter, basically. So, and this is a very neat design, because now let's say I want to change adapter. I don't need to rewrite the whole application for it to work. I only need to write a new adapter. So let's say, for example, I want to migrate from one database provider to another. I don't need to rewrite the whole core logic of my application. I only need to change this specific part, so this adapter, and basically create a new one, connect this one to the main application, which is really nice. And we do this for everything. So every time, for every need that the core has, we define a different type of port. So we'll have one port here, a second port there, and we can, for each, define different types of adapters to interact with. So going back to how this will look like. Right, so first of all, you will see the core domain we are defining here. So here in our case, it will contain the pure game rules, state, and logic. In our case, because Bevy is a Rust framework, it will most likely make sense to write in Rust. But the nice thing is really that you could really plug and play any language in principle. So you could actually write the core in Python, for example, and then interact with Bevy just through these ports and adapter mechanics. So we also have two types of ports. So we have inbound and outbound. Usually they are referred to as driving and driven ports or adapters. I, in my case, took the liberty of calling them inbound and outbound because I like the concept, or like it's much more clearer to me conceptually, because inbound ports are ports where external API or external applications want to interact with our application. So they, for example, a user interacts with in our case, with the game. So it provides, for example, keyboard input, and the outbound ports instead is something where the application wants to interact with the external world. So in our case, for example, it would be to display the information on the screen. So it will then get back and create the animation or the next frame, basically. So for this, after that, we also have a section for the initial setup checklist. So we see, for example, it wants to verify the Rust and Cargo that they are installed. Then it will install Bevy and do all of the setup that needs to be done before even starting to work on the project. We also have these conventions and standards section, which we can ask to edit, to modify. For example, based on our preferences in how to work. For example, here version control strategy, maybe we want to use a branching model. So here we see a simplified git flow model, main contains production, develop. For example, I don't like this, so I want to work without branches. So we can give that as feedback. We can set up CI/CD strategy. For example, in this, being that it's just a small test project, I don't want that. So we'll add this as a feedback. Testing strategy, this is very important. So we'll have unit tests, integration tests, acceptance tests, also pre-commit hooks, so that we make sure we are running the linters, so the format of the code is proper, and also that we are writing in an idiomatic way. And handling secrets, in this case, we don't have any, so we can basically remove this as well. I will give that as feedback. And we also have kind of this debug mode, so how we run it with debug builds. So we give this feedback, and it should update our system architecture file. And here we go. So great that we have this example to show the find and replace features. So we can either go directly in the file that it mentions and do Control F and the section and copy the replace and put it here. So we could do this, or we can do a global search. So here in VS Code, so without even mentioning the file itself, we can go in and search for a certain snippet, and we will automatically find the files that contain it, and then also view the changes. So we can see here that we are removing these sections and we are editing this part here. So we can go ahead and accept this change, and it will get implemented in the file. Let's go ahead, approve this version of the architecture. Okay, great. And now we see we will start doing the initial setup. So we can run these commands in the terminal, and we usually want to then feedback the results of these commands. In this case, it will not necessarily be needed because it's pretty simple, but we can still go ahead and do that. So also, while we wait for it to finish, why I chose Bevy is because if we ask the AI, if we open a new interface and we ask the AI what the latest version of Bevy is, you will see, without internet access, you will see it will return something like 0.13 point something, which we will see now. But basically we are quite a few versions ahead, so the current version is 0.17.4. The neat thing is that I want to show is that TeDDy is able to still work with that. So being that it works with these small dependencies, with these small iterations, it is able to pick up when its internal knowledge is not aligned anymore with the current state, when it's doing errors, and patch that and look for solutions to that. So let me go back. Another thing that we will be able to handle better, more elegantly with a dedicated script will be changes that you do locally. And if there is any editing, any changes that need to be done, it will not be aware of this edit that we have done. So it will not account for that. But that's also something that for now you have to handle manually. So let's for now just copy this last output so that the tests are passing, which basically confirms that all of the previous steps were also successful. And you will see again, we don't have any internet access here. So it is operating only based on its internal knowledge right now. The next thing that we do now is to, well, first of all, cross off the checklist because it has done all the initial setup, and now start defining the first vertical slice. So let's first go ahead and update the architecture. So we're going to be very lazy and let the VS Code handle that. And here we will create a new walking skeleton vertical slice. So again, maybe a little bit of context here would be useful. What are vertical slices? So our application has a lot of functionalities, right? And we can break this up into slices basically. So maybe we want to divide it, let's say in our game, probably we have the movement mechanic. So we have movement. Then we will also have for example, an upgrade mechanic, right? So how the snake will grow, and let's call it growth mechanic. And we will have a lot of other mechanics, right? How, for example, the damage is dealt, etc. So damage handling, for example. And all of these mechanics go through all the layers of our application. So from getting the input from the user to handling that input and then outputting it in a visual form. And the idea is that we handle each of these vertical slices one by one. So we don't go ahead and first implement the whole user input logic. So this would be the alternative, like the other way to handle this, which would be to handle the application, to slice the application into horizontal layers. So we could have here user input, and we could have, for example, now the domain logic, and then we could have the output, so the rendering basically. And the alternative way would be to first define the whole user input going across movements, growth, damage handling, etc. And then define the core domain logic regarding movement, growth, and damage handling, etc., etc. But the thing is, we don't yet know everything that we want to do. So maybe while going ahead, we actually iterating upon the game, we find that we need to change something, and going through these horizontal layers means we only at the end we get feedback on how it's working. So only after we have done user input, core domain logic, and visual rendering, we have a way to visually interact with the game and validate that the movement, the growth, the damage handling is working as intended. Instead, if we work with vertical slices, at each vertical slice we have the occasion to provide feedback and to review the output, or like how things are working, and to guide the design of the application of the game in this case. So after this little tangent, let's review how these vertical slices are actually defined. So we have, first of all, we always start with a working skeleton. So working skeleton means basically end-to-end slice, which doesn't have, we are just connecting things and making sure everything is working properly. So in this case, it will be very simple. We just have one scenario. So the application runs and exits cleanly. So we want the application to be compiled, the user to execute the application, a black screen window to open, and after that, we close it and we exit with a proper status code. And even for something this simple, we still need we have different components. So you will see here, we need to create the domain model, the inbound port, the outbound port, inbound adapter and outbound. This is basically how it always looks like. And we will see here the different ports that we need to define. So the domain model we need to define in its whole. The tick port we want to create as an inbound port. You have an exit port, and we have a Bevy tick system and the Bevy exit adapter. And here you have an overview of how the different components interact. But right now, without going too deep into it, I would say we can proceed and see what the next steps are and how this all plays out basically. So now for each of these components, we will define in a different doc how these components look like. So in this case, for the domain model, as mentioned, we will write it in Rust. Something also important for a domain model is to always have an ubiquitous language, which is a way to define basically the glossary of how we talk about the application in a unified way, so that we can interact with the AI also being very precise and knowing that we mean the same things. So in this case, for example, being that it's still at the very beginning, we have just this word defined, so a tick. So we will see what this means is a single discrete update of the game state. In the context of the working skeleton, represents a single frame processed by the game engine. So we now know how to refer to this in an ubiquitous way. And we also will use this language across the code that we create. So we will use ticks as our kind of a keyword that we use across function names, component names, etc. And this helps us to always know what we are talking about. Okay, so we can move forward. And of course, if you want, you can always here guide the direction in which you want the AI to go with. So you don't necessarily need to adhere to everything the AI says, but you have a very focused way to guide it before it just does things, and it has already created all of this code, which is really difficult to navigate. So what we do now is we create this tick port document. And here we see the tick port, which, as mentioned in the diagram, will be basically the access point for the game, or like for Bevy to signal to the core that a new tick has happened, basically. And again, you will see we do not define anything that we don't yet need. So we are not defining methods and functionalities that are not needed yet. We just stick to this initial working skeleton, and the idea is that we will figure out what we need as we go along. So we now have this exit port defined as well here. So this is basically to exit the game, and we proceed. And for each of the methods, you can then trace back from where it came from. So you will be able to see that it came from this first vertical slice, and you can track back from the slices basically what was the expected behavior, why it was created, and yeah. So now what we want to do is for each, so we have defined these components, we have defined the ports, the core domain model, and exactly the ports in how the core will interact with the outside world, with external frameworks, in this case with Bevy, which will handle the everything else, so the user input and the rendering. But now we want to create the adapters that interact with these ports. So we want Bevy to be able to interact with this tick port and this exit port. And to do that, before, let's say, handing over to development to actually implement this first working skeleton, we want to de-risk the implementation. So we want to make sure that we understand how this external application works, so that we interact with it in a proper way. So what we initially do is a round of research, and after this research we will test the implementation with a spike experiment to make sure that the information we have gathered is actually working as intended. How I handle it currently inside of TeDDy is using these basically search engine queries. So you will see with this research action, the AI gives us some queries to search for, and we can now go ahead and execute them manually. I use DuckDuckGo. What we want now to feed to the AI is this search engine result page, so that we get all of these links. Instead of having to do that manually, I've written a small script to do that, to handle both Google and DuckDuckGo, which is my preferred search engine. And basically using this bookmarklet, which is basically just a script inside of a bookmark, you can, on a search engine result page, just execute it and copy the results to clipboard. And now we can paste it, and this only provides the links for now, so not the content of the pages. And we can do this for the second query as well. What the AI knows that needs to do now is to read the pages that are most useful, or that it thinks it would be most useful. The thing is, you can, for example, also use URL context in Google AI Studio. You could even have grounding with Google search, but why I'm not doing it is, first of all, we want to control the context as much as possible. Here, using grounding and URL context, we don't really see what it's doing. And also in the future, the idea would be to be model agnostic. So we want to be able to use any model that we like, even local models, without needing to have these built-in functionalities of grounding with Google search or URL context. You're of course welcome to experiment with it, but it's not designed to really do that on its own. So what we now do, what the AI now does, is it wants to read the quick start, getting started page. So we can open it here for reference, and to feed that to the LLM, there are many conversion tools. I happen to use this one, but there are many others which also work pretty well, where the page gets converted to a markdown, which is the native language of LLMs, and basically we can then just copy and paste it in. Something else I often happen to do is, if we have a very big output, for example, in this case it's not too bad, but if we see we are already reaching a lot of token usage, we are getting the AI starting to struggle with this big context size, we can also delete this raw output that we provided it, because once it has read a new source, it will summarize what it has read, the most important information. So you will see that the application has provided two critical pieces of information, so defining the system and registering the system. So you will have that as part of the context anyway. So you would be able to actually delete this output without really compromising the performance of the LLM. So actually, for the sake of it, let's do that. And you will see now, basically we have the read action, and it goes on with the next one, but this, we can move forward with this. We could even remove the links, but I think this could be useful for it to use in the next iterations maybe, because hopefully there will be other bugs and the issues it will run into, so that we can see how it proceeds to resolve them. So as mentioned, we now want to create really a proof of concept that this information that we have gathered actually works, and hopefully actually it won't work, because that would be the most interesting thing to show. And actually we have this, so we have expected outcome. We have a self-correction during planning. So actually it's caught that we first need to add it there, which is interesting. I don't often see this self-correction. So actually we want to go into cargo and we want to edit this. We can also, in this case, pretty simple to find this line. We can just paste it in. Perfect. And now we can run it again. And so we have an error, which is great, because this way we can kind of experiment and see how the AI handles the resolution of this issue. So what it should now do is change the color of the status, because now we have an unexpected event. It was expected to run, so this is an unexpected event, so it should now become yellow, and we should actually now try to debug the issue. So we see here an error analysis, and this is where I would pay more attention to what the AI is doing, to kind of intervene before it's too late. You can always go back, which is also a nice feature of Google AI Studio. You can always go back and branch conversation, so you can go ahead and try to find a solution to the issue yourself, identify what the issue is, and make it basically implement the solution without risking to kind of pollute the whole context window. And once you have found the solution, you can go back and delete useless messages or something is not needed anymore, and that's really useful. So you can see here an error analysis. So this assumption is actually not correct, because we are not using a later version, but let's see if it resolves it, if it's able to. Go ahead and edit it and see the changes. Okay, interesting. Let's see if this fixes the issue. So now we can run this again, and it still doesn't work, but I think the error message is different this time. So now it has tried to solve it. Let's see if it tries again, or if it looks for more solutions online. Okay, so we see here an uncertainty, which should result into a research, exactly. So now we have some new queries to execute, which we can do. So this is the first one. We can go ahead and do the second one as well. And also, I forgot to mention, but these bookmarklet scripts I will also have in the repo that you can use for yourself. So you can just copy the code, JavaScript code, and save it as a bookmark, and then execute it as well. So let's see with these links what it will do. Okay, so I think it has identified the best resources to access. We can go ahead and read this URL and convert it to Markdown. So here you see we are at 45,000, now we are at 57, so it's more than 10,000 tokens, which is significant. So you will see a lot of this is kind of garbage. Go ahead and remove this, I would say. The AI should even be able to suggest you to the context, but it doesn't always figure out what it means for an output to be very long or not. So let's see. And of course, the nice thing of using this is that everything we are doing right now is free, because we are inside of Google AI Studio. Right, so now we have read the documentation and we want to implement this solution. I will go ahead and delete this from the context so that we save some context window, and we can go ahead and implement the new changes, if we can find them, of course. Doesn't seem to be the case. Let's go in manually and see if we can find it. So it's this snippet here, but for some reason it doesn't find it. Let me manually check why. I think probably it has something to do with the indentation. It's not great, but this is something that you can either manually go in and adjust, or in the future version we would automate something like this. So now that we have found the correct snippet and we correct the indentation, we have implemented the changes, and we can go ahead and run it. Let's see if it is resolved. Great. So we actually get it to run. And so we now have confirmed how the system should work, right? So how we actually interact with it. And you see the value of actually proceeding in these small iterations, because something like this, if the AI would just go ahead and create the whole code from the start, it would hallucinate how this actually works. as it did actually, but we would never catch this. We would only catch this at the very end when the code is already very messy, very complicated. And once we see this bug, the AI would kind of freak out and look all over the place for solutions, and it would be really difficult for an AI or even an expert developer to really identify where the issues lies, unless you really know what you're doing. And instead, like this, because we proceed with these small iterations, it's very simple to identify where the issue lies and search for solutions, because the issue needs to be in what we have just created, just written, and it's just a very small piece of code. So now, as being that we have validated that this works, we can now go ahead and document the plan for the adapter. So now we can go ahead and paste this contents, and we can see first of all we have the external documentation connected, so we have the quick start here, and we have also the spike connected. So this will also help the developer prompt to review it and be able to see how it should be implemented. Great, so let's proceed. So now we proceed to the next adapter. So we have this outbound adapter. So what we have now initially defined is this inbound adapter, which in turn implements the inbound tick port. And now we will do an adapter for the exit port, basically. So we can go ahead and copy the file path to create the file and create the document for the outbound adapter. So because we have verified it with the same spike, we don't need now to do a different one. We just connect. You will see we refer to the same spike, and here we have the exit documentation from which we got the information for it. But of course, if it would have been a different system that we are interacting with, for example, Bevy for input, and we can use Godot as the rendering machine. In this case, we would have different spikes, one for Bevy and one for Godot. Great, so we proceed, and now we should just wrap things up and then start with development, basically, which will be very easy in this case. Again, we are proceeding with very small steps, but it saves you much more time than speeding through it and then needing to debug everything. So we can go ahead and update now the vertical slice document. We can even see now the changes for it. So now it's done, and we have added the architectural components. Okay, great. So next step, handoff to development. Great. So yeah, I would then each time we switch, I would always try to manage the context. So managing the context is very important to not get the AI derailed. So if we don't need it, we should start a new conversation. So so that we have always a clean context window, making sure we deactivate anything that we don't need, and we have selected the correct model. And now we can start with the development. So in this case, of course, we are starting a new project. It's not so flashy as you see when using, for example, Cursor or Cloud Code, but it is reliable. It's much more reliable what you build than what you get from these vibe coding tools. So right now, let's start with the development. To give it context, first of all, I use this plugin, which is also linked in my repo, which is Copy4AI, where you can select files and copy to clipboard, or also just copy the project structure. And it's very useful to pass the information to the AI. So right now, let's just pass this, the README and the docs, because we know everything is relevant. We could just also pass the project structure, and the AI would then do the actions of reading the files that it needs to. But for now, because we know what the AI needs and we want to avoid this unnecessary step, we can give it the whole docs, and even let's give it even the spikes as well. So basically almost everything, and we can copy this, paste it, and go ahead with it. So you will see this plugin, it gives you the project structure, how it looks like, and then for each of the files that we have selected, it will also provide the contents of it. Of course, again, as soon as there is a working implementation of this companion script, let's say, which allows you to execute the actions directly, it would basically pass directly this context, so it would handle this without the need for external plugins. So we see TeDDy is asking right now to read the cargo.tml, so we can copy that. In this case, I have the project structure still being copied. I can remove that and just pass the contents of the file. So we can just go ahead with this. TeDDy doing is also handling the version control. So right now we have not committed anything, we have not added anything. Maybe I could improve this to make the architect also commit its changes. We could do that ourselves, but we will see TeDDy will do that. We will handle that as part of its process. Perfect. And now we see the test is failing, which is, you would think it's a bad thing, but actually this is part of the test-driven development cycle. So you will see, so first of all, we have different phases. So this is the whole, let's say, task list that the AI has. So it first wants to create this acceptance test, then implement the inbound adapter, implement the domain model and the core logic, and then implement any outbound adapter, do internal verification or refactoring, then showcase this with us basically and polish it, and then document it and commit. So this is the outside loop, the outer cycle, where it's right now implementing this functionality so that the application runs and exits cleanly. And within each of these phases, we have a cycle of red, green refactor, and then we add the staging, so the version control. And this helps us basically to apply, let's say, the scientific method to programming. So we first start with creating a hypothesis, how we want the code to behave, and we already this is a very crucial step for the design of our code. We really define how we want to interact with these components that we are going to create, and then we actually create them. It's very important to write the tests first and only then the implementation. And then we can verify if actually the code does what we were expecting it to do. And after that, we then refactor it. So in the green phase, we try to create the minimal implementation of the code, and only after that, look for opportunities on how to make it more readable and more idiomatic, more maintainable, etc. So right now, we were in the failing state, so in the red phase, and we now actually want to implement the changes. So actually we're staying still in the red phase, and now we go in and we edit the main source file. Also here we cannot see actually we want to replace the whole file. So we will go in, replace the whole contents, and also create this new file for the core. Create a core domain file, one for the ports, one here. Let's just go ahead without reviewing much, but of course, in the ideal case, you would review the structure and also give your inputs about the structure of the file structuring, design of the code overall, etc. So now we are updating the cargo file. You can see the changes here. It's correct, yes. Perfect. Let's now run it. And we see we have errors, which is good because we are still in the red phase, so we are expecting it. Or actually, we were not expecting it in this case. I predicted a single unresolved import error for the Bevy tick system function. Instead, I received two different compilation errors. So this is also interesting because we want to predict how the code will fail. So not only that it fails, but also how. And in this case, it didn't predict it properly. So we were predicting a compilation error, but evidently we got something else. So great. To fix this, let's see what it tries to do. So we want to first now fix, we want to create this file. let's go ahead and do everything that it asks us to do and see how it works. So we do everything here, create a new file. And this is very useful data because also here, if the test already fails in a different way than what we expect, it's already a signal that we are operating with false premises. So it's already a good point of revisiting our assumptions, or for the AI to revisit its assumptions before we kind of start to work with these and go too far ahead, and then it's very difficult to do that. Let's see if now we are getting the error that we were expecting, or maybe not. Let's see. It's thinking a lot. Okay, so here we see we expected outcome failed, but in a way that revealed a deeper issue. Okay, interesting. Let's see if it's able to resolve it. Okay, so here the AI is basically asking us to step in. Implement the exit port using the recommendation waiver. If we go in to the adapters, exit adapter, let me just give it this, maybe, what it thinks of this. Okay, interesting. Maybe we should have, either the AI needs to be smarter to look at the needed spikes, or we should have passed the relative spikes for it. As mentioned, it's not perfect right now, how it handles things, but it's already much better because we are able to identify these issues, in my opinion, early on, before it just creates something uncontrollable. So I actually want to keep these small issues that we see as an example in this video to show you it's not perfect, you need to review it, but it's much, much easier to do that. So let me see. We are now adjusting here. We are probably implementing now the change according to the spike. So actually, this is also a good point why we do these spikes, right? So that we really understand how the system works before creating the actual application that depends on it. So replace all the contents here, and now we execute the test again. Let's see. And we should be passing the test, which is the case right now. So we have a good success case. Perfect. So the teaching here is we need to read the relative spikes before starting to develop things. Perfect. Version control. So now we are already, we have already written the acceptance test. We can stage now the changes. So now it's only adding source and tests and cargo.tom files. So we haven't added everything. We have still this. So actually I will go ahead and add everything as a stage to the staged changes. But actually, I think in the future, it would make sense for the architect to add and commit the document changes before starting development. But these are the kind of kinks that I'm still trying to figure out as we go. So this might seem everything is very overkill right now for this initial setup. We are going forward in baby steps, very baby steps, but it sets a very solid ground foundation for our application. We know things work actually and why they work, and we have everything really documented, and it's really easy to build upon this. So that's the idea. So we go ahead and create this, include this directory, perfect. And then we execute again. This time it should fail, which is the case. Let's see if it failed like it expected it to. The minimal code, and we execute the tests again. Now it passes, which is great. So we will see we have added now the changes to staged, and we can proceed. All right, so as the video was running long, I decided to cut it here. I'll be making some progress in the meantime off screen on the game, so that in the next video we can jump in a more advanced state of the project. And I think it's also very useful to see how TeDDy behaves in a more brownfield situation. So also a couple of things I will be working on in the meantime will be improving the feedback loop between the developer agent and the architect agent, and also introducing a third agent for for debugging so that it can handle these more complex issues without disrupting the main development flow and its context window. So yeah, if you like this video, make sure to subscribe so you don't miss the next one. And I'd also love to hear your experiences in the comments down below using TeDDy. So thanks for watching and see you then.